Welcome back, and we're going to continue on with our studies into mathematically calculating Kc values and using that to express what we know about an equilibrium system. So today we're going to look at determining values of Kc where we haven't been given the concentration values for the equilibrium system. So this might be just determining how something might affect the value of Kc, or it also might be how we can calculate Kc when we've been given a reaction and a value for Kc and that reaction has changed in some way. So a key thing about looking at our equilibrium constant K is that it is very dependent on temperature. So the value of Kc, the value of Kc will not change for any reason other than temperature. Okay, so nothing will cause Kc to change unless we change the temperature, and then it's very predictable in what will happen to it. If we increase temperature for an exothermic reaction, then this means that the amount of products decreases. This is because if you think about it, for an exothermic reaction, we have an excess of heat. That's going to favor the backward reaction, which we talk about with Le Chatelier's, but essentially it's going to decrease the amount of product that we have available. So for an exothermic reaction, when we increase temperature, then the value of K will decrease. For an endothermic reaction, the opposite happens. If we increase temperature, then we're going to increase the amount of products. So the value of K increases, remembering that we've got products over reactants in our Kc value. So if we are increasing the amount of products, then we're going to be increasing our Kc value in this case. So it is important that to remember that the only thing that will change the value of Kc is temperature. Changes in concentration, changes in pressure, nothing else will change the actual value of Kc, the mathematical value of Kc, except temperature. That also includes adding a catalyst. Okay, and this is primarily because when we add a catalyst, we actually increase the rate of the forward and the reverse reaction at the same time. So the only thing that changes Kc is temperature. It often comes up and tries to trick you, but unless they're changing temperature, Kc will remain the same. So this brings us to units, okay? And units for the values of Kc can seem a little bit daunting in some ways, but it is important to remember that with any unit, they're mathematically derived, and the same thing goes for the value of Kc. It's just because of the nature of the calculations that we can end up with something that seems a little bit funky. So the values of the units of Kc are some variation of concentration, because all the terms that we are looking at are in concentration, but they won't always cancel each other out. So we can end up with our molar concentration squared, or we can end up with no units at all, depending on how many terms we're working with. So if we look at this example here, we can write the value for Kc, and then if we substitute in this capital M for molar, which for us is moles per decimeter cubed, okay, but if we keep it simple and keep it to the symbol, we can see here that because we have the molar concentration of NO2 squared, this would become molar concentration squared divided by the molar concentration of N2O4, so divided by molar concentration. I'm going to, using indices laws, when I divide, I'm going to minus 1, so I get M to the 1, which is the same as M, which in our case would just be moles per decimeter cubed. Okay, so if we look at the one here where we write the equilibrium expression for Kc for the reversible reaction of this, we would end up with Kc is equal to the concentration of SO2 squared multiplied by the concentration of O2, and this will all be on top underneath concentration of SO3 squared. So now if I substitute in to work out what my units are going to be, I'm going to get m squared on, this is 2 plus 1 is going to be m cubed, which when I cross it out, I'm going to get 1. I'm still going to have 1 under here. So I'm going to get m to the negative 1, because it's going to be 1 over m. Okay, so now we need to put that from moles per decimeter cubed. So that's our molar, and this is all to the negative 1. Okay, so we're going to end up with mole neg 1 dm3. Okay, because we're going to multiply this out here, okay, to get our overall units here. These can look a little bit confusing. They take a little bit of practice, so make sure that you're calculating your units anytime you go to calculate a Kc value. So again, we're looking at another worked example here, and we're calculating the equilibrium constant for our N2O4, and because we are here, we're deciding if it's at equilibrium or not, and predict the direction that the equilibrium will shift. So in this case, we're told that we have a reaction quotient. We're going to work out the concentration of N2O4, which is 0.2 mole in a 2 molar in a 2 liter vessel. So this gives us 0.1. And then we're going to work out the concentration of NO2. So the number of mole divided by the volume. So the number of mole, again, divided by a 2 liter volume because they're gases in a container. And then we're just going to substitute those into our expression, which is the same as the one we saw before, which is NO2 squared over the concentration of N2O4. So we get NO2 squared over 0.1, which is equal to 0.23 molar. Okay, which if we have a look here, again, we have that m squared over m. It's going to equal to m, which is equal to moles per decimeter cubed. Okay, so if we have a look at this, this is Q because we knew it wasn't at equilibrium. It says it's at 0.23 molar is our equilibrium constant. Okay, and we have to decide if it's going to move to equilibrium or away from equilibrium, in what direction. So for that we need the value of K, which we were given in the previous one, and we can see that the reaction quotient to equal K, the concentration of NO2 must increase and the concentration of N2O4 must decrease, which means we want to use up the reactants and push it towards the products because we're heading towards this 4.5 molar, and this is lower, this is less than 4.5, so we want to push it in the direction of the products, which means that the forward reaction must occur. And that's how we use Kc and Qc together to predict which way equilibrium will shift. What I want to talk about here, though, is how we can work out what Kc value is if we haven't been given the concentrations. So if we look at these reactions here, again between NO2 and N2O4, there's a number of different ways we can look at these equations. We can have N2O4 decomposing into 2NO2, which gives us the equilibrium constant here. Or we can look at the reverse reaction, because remember that the equilibrium constant is specific for a specific reaction, so whether it be forward or reverse, at a specific temperature. If we change that, then Kc is going to change if we change anything about the reaction. So in this case, we're now looking at the reverse of this reaction as our primary reaction. And we can see that what's happened is we've got the inverse here, which mathematically just means that we have taken 1 over K1 to get K2 here. We've taken the inverse of the reaction, so we can take the inverse of the K value. In the case of this one here, we've halved the coefficients, which means that in this case, we have actually risen all our powers to the value of a half, which means that what we've done from K1 to here is actually taken the square root of it. So our indices at laws apply to our Kc values, and there's a really good table that shows this on page 132 of your textbook and goes through also what happens if we double the coefficients. So remember, if we double the coefficients, we'll be changing all our powers here by a factor of 2. So we'll actually have to square the Kc value. Okay, if we reverse the reaction like we did here, we take the inverse, and if we halve the coefficients, then we're taking it to a power of a half, which is the same as the square root. So those mathematical functions work exactly the same on our Kc values as they do for anything else, and it allows us to work out what the value of a Kc would be for a specific reaction if we haven't been given the exact concentrations at equilibrium, but we do know the Kc for the original reaction. So, just summarizing some of that, remembering that Kc gives us the extent of reaction. So this is the numerical value telling us how far the forward reaction has gone. So a couple of quick rules of thumb on that is if our K value is very large, so greater than 10 to the 4, so 10,000, we're looking at mostly products. If K is very small, so less than 10 to the negative 4, then we're talking about something that's mostly reactants. And if it falls between these values, then we tend to say that it's relatively even and it doesn't tend to favor the forward reaction or the reverse reaction heavily in either way. So examples of that, we can look at the reaction between the strong acid hydrochloric acid and water to give us H3O plus and Cl minus. And here we know the strong acid pretty much dissociates completely at 25 degrees C in water, and this K value would indicate that. We have 10 to the 7 at 25 degrees C, which is telling us that it is mostly products. Whereas if we contrast that with a weak acid, say ethanoic acid that we have here, we can see that our K value is 1.8 times 10 to the negative 5, which is putting it firmly in this mostly reactants category, which goes along with what we understand about weak acids. Okay, so just remembering that Kc is giving us a numerical way to describe how far an equilibrium position sits towards the products, and that we can use our mathematical index laws to manipulate that value if we have the original equation and are lacking our concentration values. So have a look at your textbook questions. Make sure that you do them to get some practice and you have some extra questions as well. And good luck with your practice.